Why do golf balls have dimples on them?
The reason is twofold. First, we'll explore the lift. The Magnus effect generates lift on spinning bodies with circular cross sections. The dimples on the golf ball amplify the Magnus effect, but they don't generate the lift. Deeper dimples will be pockets of air, which aren't aerodynamic, so generally we want shallower dimples. With larger dimples, the ball's behavior approximates a smooth ball. The number of dimples is not important. The behavior is summarized with a dimple depth ratio, and when you optimize it, you'll get the desired lift and drag you want. The Magnus effect on a smooth sphere can generate negative lift at medium ball speeds, but it's usually positive at high ball speeds. Positive lift arises at high speeds for smooth spheres if the angular to linear velocity ratio is less than 0.5. Relations on this slide display this threshold for smooth balls. 0.6098 inverse inches is obtained from the average ball diameter of 1.64 inches. Note that the ball here rotates clockwise. Here's a photograph visualizing the trajectory of air around the golf ball. As you can see, it's similar to a wing. It's been shown experimentally that when a golf ball has dimples versus when it doesn't, at a given flight speed and spin rate, the dimpled ball will generate more lift force. The main reason, however, why golf balls have dimples is because they reduce drag. In order to reduce drag, ultimately we want to reduce the area of turbulent flow. Here are some equations that will be important. On the first line is the drag coefficient, which is the ratio of the drag force on the ball over 1/2 the density of air times the free stream velocity squared times the cross-sectional area of the ball. The second line is another dimensionless number, the Reynolds number. This is the ratio of the free stream velocity of the ball times its diameter over the kinematic viscosity of air. For the average golf player, the Reynolds number is going to be 150,000, which is a diameter of 1.64 inches at an average speed of 125 miles per hour divided by the kinematic viscosity of air. In the third equation, we've rearranged the first equation to solve for the drag force on the ball. In the fourth equation, we've replaced the Reynolds number into the expression for the drag force on the ball, giving us the drag force on the ball as a function of its Reynolds number and its drag coefficient. In this graph is experimental data that's been recorded with balls of varying roughnesses. Here we see the drag coefficient is a function of the Reynolds number. The phenomenon of the drag coefficient sharply decreasing is known as the drag crisis. This is helpful in golf and other sports with aerodynamic projectiles because it decreases the drag and allows for higher projectile speeds. Since the drag coefficient and Reynolds number are non-dimensionalized, the location of the drag crisis is only a function of the sphere's relative roughness. Increasing the relative roughness shifts the drag crisis towards lower Reynolds numbers, which is desirable for golf balls where the Reynolds number required to reach the drag crisis isn't reached naturally when the sphere is smooth. Turbulence has higher kinetic energy than laminar flow, but lower static pressure. This relationship is given by the Bernoulli equation. Spheres see an adverse pressure gradient as a result of the no-slip condition at their surface. This causes velocity in some regions to point upstream, as shown on the top left diagram. The point where the adverse pressure gradient and the forward pressure gradient intersect is the point of separation, which has minimum pressure and marks the beginning of the turbulent region. Lower pressure behind the sphere, relative to pressure in front, pulls the ball backwards. Golf ball dimples create localized pockets of turbulence, which result in a much tighter boundary layer, as shown on the bottom left diagram. This in turn pulls the free stream region closer towards the ball's surface, decreasing the turbulent region. This is seen on the diagrams to the right. When this region is smaller, the pressure differential will act on a smaller area and therefore result in less drag force, represented here by red arrows. A good way to visualize this phenomenon is the wake of a boat. In this photograph, on the top, we see a smooth ball whose separation point is closer to the front of the ball. This creates a larger turbulent region. On the bottom, however, we have a ball with dimples, whose separation point is closer towards the back of the ball. We can see that this creates a smaller turbulent region. From experimental data, we can see that at a given spin rate of 3000 RPM, for different flight speeds, the dimpled ball is going to have exponentially less drag force than the smooth ball. If you're interested in reading more about the topic, here are some sources which we used to make this video.
Thanks for watching.